Okay, so we have a tuple, and in that tuple we have a set of states, Q, the alphabet. This delta function, which is very important, is the transition function. This is the initial state, S, and a set of final states, F. So we call this a deterministic final state automaton. And notice that there is only one initial state, and there might be several finite states. Okay, so you already remember what the alphabet is. The alphabet is the set of symbols, and then we're gonna form strings over that alphabet. The delta function is a function that goes from this set, the Cartesian product of the states and the sigma, to the set of states. What does it mean? Basically, it means that this delta function gets some state, let's say, they call it P, and a symbol of the alphabet, let's say A, and this function will return the next symbol, so let's say Q. That means that if you are state P and you read the symbol A, the next state will be Q. So basically, that means that your automaton has this transition. P, A, Q. That's basically what this function does. It tells me, given a state and a symbol, the next state. Of course, this P could be equal to Q. So in that case, you will have, if P is equal to Q, you will have something like this. You will have a loop. Okay, so any questions regarding that? Juan Floyd, do you understand this?
Yes, teacher, I understand.
Okay, good. So then we'll have some special state. Remember the start state or initial state. And you draw that like this. Okay. And you have F, which is a subset of Q. And those are called the accepting or the accept or final states. Okay. So, for example, here we have, let's say that my set of state is this one. So in this case, my Q will be 0, 1, 2, 3. The input alphabet, let's say that is A, B. So that means that sigma is A, B. And the start state is, let's say, is 0, is this 0. So in that case, S is this 0. And the accepting states is only this set. So it means that you only have one accepting state. So F is 3. And then I specify the transitions. I say, if I am in 0, in the state 0, and I get an A, I move to the state 1. If I am in 1 and read an A, I go to state 2. If I am in state 2 or state 3 and I get an A, I move to state 3. And this is the picture that you get. So my states are here, 0, 1, 2, 3. So just to verify, what will be delta of 2B? Let's say Natalia.
Sí, profe.
Can you answer this? What's delta 2b?
Tarea 2, el mismo.
Yes, very good. Okay, so this is basically how you specify this. In order to specify the delta function, you can either give this long list of all possible incomes, all possible inputs to the function, or you give it as a matrix. Do you know how to read this matrix already? Arango? Arango?
Sí, profe.
Do you understand how to read this matrix?
Sí.
Okay, so just is a usual matrix, so it tells you that in state 2, if you read an A, you move to state 3, and if you read a B, you move to state 2. And then you mark which one is the initial state, so you do this, and you mark with an F all the states that are final or accept. In this case, there is only one, which is the number 3. Okay, so this is clear. Now we want to do something a little bit more complicated, but I'm sure you can do it. So here you understood that delta of, for example, 1a gives me a 2, right? Now the question is, what would delta of 1, let's call it delta star, of a b? You try to understand this. I haven't defined that properly, but basically the difference with this delta star is that here the input is a symbol. It's a symbol from the alphabet. Here's string over the alphabet. So it could be many symbols. So what do you think would delta star 1AA be? What would be the natural answer to that, Santiago? Santiago?
Yes. That one would be, I believe, 0?
No. Natal,
2
Nicole.
maybe?
Nicole?
Would it be 2, 2?
One, let me see. No. No. Another Juan Sebastian?
Creo que haría 3.
Exactly. So this is basically, if you are 1 and you read 2 A's, I mean A, then you get to 2 and the second A leads you to 3, okay? This is, do you understand this, Nicole? Now? Why is,
Yes, teacher.
okay. Now, here is the question. How would you define delta star? Let's say we want to define delta star inductively as follows. We want to define delta star in terms of P and a string, an arbitrary string, let's say X. And we want to take two cases. So as usual, inductively, you say the basic case is what will happen in the empty case when the string is empty, and what will happen if the string starts with an A followed by X. So this is a string, empty string, and this is a string that the first symbol is A, and the rest of the string is X. Any ideas?
The first one would be P again?
Jeremias? Okay.
Yes.
The first one will be what?
P.
Yeah. So basically saying if you are some state and you read nothing, you stay there. That's nothing is the empty sequence. Okay, and what happened in this case? You are reading a string that whose first symbol is A. You can use here what you already have, which is delta, the single delta.
That maybe that could be like having delta of, and the starting point could be delta of BA, and then the second part of delta is X.
So, okay, so what will you exactly write here? Like,
I mean,
can
like
you
open parentheses, delta of I mean, outside another delta. Sorry.
outside what?
I mean, delta parentheses delta.
Outside delta, just delta?
No, delta parentheses delta. So, I mean, you have one delta, now parentheses, another delta, parentheses, P, and with the string A, close that, and the string that has the first delta is X.
Very good. Almost very good. So what do you think you're missing there, John?
Maybe the asterisk of the first delta
Star. So the star, where does it go?
and the first delta.
Very good. So, okay, this definition works. Now, can you explain, like you would explain to your fellow students, how it works or why it works?
Yeah. So, like, I think about this like I'm doing some steps. So let's say I start in P and I want to move to the next state that tells me the string A, right? So when I do that move, the point of where I'm now, that will be like the next like starting point, and then I could do that again and again and again.
Very good. So basically, I'll try to draw the idea that you got here. Let me see if we have a better example. Yeah. Sorry, I call it delta star, but in the book they call it delta hat. So just remember that. So this is the delta hat, and this is the definition that Joan came out with. And just this is the example. Let's suppose that you want to find out in this state, Q, where you go after reading the string A1, A2, A. Okay? So, okay, so sorry, this is the other definition. Like it's an equivalent definition. Let's try this definition instead. I'll make a simple example instead. So we have P, and let's say we have Q, and we have R, and we have S. Okay, and this will be, let's say, A, B, C. So what should delta I'm gonna change the name right now, delta hat, which is the same as delta star. So delta hat of, let's say, P with A, B, C. We all know what it is, right? This should be S. Is that clear, Natalia? This is
Sí,
clear.
profe.
Okay, now we're gonna just explain the definition that Johan gave. So Johan says, how do you compute this? He says delta hat of P, A, B, C is the same as delta hat of delta of P in A followed by BC. That's what he did, right? Now, this part here, it tells me that the next state here is, what's delta PA? Juan Esteban, what's delta PA there? Santiago?
Should it be A?
Yeah, no. I think you know the answer, but you just read wrong the symbol. It's Q, it's the state.
Sorry, Q. Yeah.
Okay, so that's basically basically the idea that Johan is using is that of a path. He say to go from here to here, first I go here. Okay, so this delta PA gives me this Q, and then you continue with BC, which is this part. So do you understand that definition now? This definition here?
Yeah.
Okay. Now I think you all got it. And now this thing here was that in the last semester, I think, another good student came up with a different solution, which is different, but it's equivalent. He said something like this. He said, delta hat of state EU, well, I'm gonna change this U, not to confuse you. He said Q, what did we use? P, I think we use P. P epsilon is P. And then he said delta hat of P XA is, it's complicated to read this little part. Look at the differences. This delta is outside and the delta hat is inside. He said that is delta of delta hat of px followed by a. So this is another definition that, can you explain why it works?
Maybe because the delta hat receives a string, and the delta without a hat always receive a symbol. So if you solve that like recursively, it will be the same output.
Exactly. Exactly. So this is like the other way of doing it. So we have two definitions. I'll put them here. This is this one, and this is the other one that we just saw with Joan. I think I have written here Naim. We were supposed to be before working with us. And now one homework is to prove that these two definitions are equivalent, okay? And again, you can do this by induction. Okay, so now you understand these definitions, I assume. Okay, don't look at this because this is the solution. Now we're going to define the notion of acceptance. We say that, actually, let's try to do it ourselves. That would be better for you. Remember that an automaton M accepts a string. Let's do an example, draw the typical example here. Let's call this the state S T 1 1 0 0 and this one, yeah. Okay, so remember, for a string to be accepted, you have to start in the initial state and go into a final state after reading all the string. Okay, that's why the string 1 1 1 is accepted. That means that the string 1 1 is not accepted. Okay, so now you have all the tools to define mathematically whether string is accepted or not. That's what we want to do. So M accepts the string X if and only if what? Any ideas how to do this? Jeremias?
If the string is, how do you say, impar, even?
No. This was just an example.
Okay.
I want you to define in general for any automaton M whether it accepts X or not. John?
It will be if the delta of Sx, the answer for that is inside the set F.
So exactly, if starting from the initial state X leads you to a final state, okay? In that case, for example, we can see that delta hat of 1, 1 is equal to S, and S is not in F, because here my F will be, sorry, T. So 1, 1 will not be accepted. Sorry, I forgot to write the initial state here. But delta star from S1, 1, 1 is equal to T, which is in F. Okay? Any questions there? Okay, so I assume that this you understood. Now the other thing was the language of M. The language of M, remember that intuitively we said that was the set of all strings. In this case, for example, as Juan Fernando pointed it out, are all the strings, all binary strings with an even number of ones, right? So the language of M in general will be, how you define this? with the tools you have already there. Any ideas how to define that? In general, L of M. Jeremias?
I'm thinking.
Okay.
In that case, or
Yeah,
in
no,
every
in general.
case?
In general.
In general.
Like, here is this is a general definition for doesn't matter the automaton. Basically, you have to write down mathematically what I'm saying. It's a set of all strings that are accepted by M. So how you write that as a set?
Like maybe X
Mm-hmm.
such that
Mm-hmm. Such that
with the delta function.
exactly delta. I
Yes.
start delta hat. I wrote.
Delta hat, yeah.
I always write this star here because I usually call it delta star, but this book changes that notation, so it's okay.
How do we represent any initial state like with S? Okay.
Yes.
S and X
Mm-hmm.
is in F.
Exactly. That's the language of automaton. So now you have defined formally what an automaton is, a finite state automaton, I must say. And now we define what a regular language is. So we say that a set A is regular if there exists an automaton M such that the language of M is A. So that's exactly what a regular language is. The typical question is this language regular? If the answer is positive, you need to provide, let's say, or to show that there exists a automaton whose language is A. Or if it's not possible, you need to show that there is no automaton that can accept that language, okay? So any questions about these definitions?
Can you go back to the
To the what?
like the word, like the where we have the language thing?
Okay,
Oh,
here.
thanks. Just a moment.
Do you have a particular question or?
I was just thinking like, what does like regular mean in this case? Like, it's like the pattern of what we saw the last class, or?
It's basically a definition stating whether regular, I mean, the word regular is just given to the languages of automaton. It's just a name. It could have been called, I don't know, any name that you can possibly come up. It's called just regular. It's just a definition, okay? I suppose it has to do with that the patterns are somehow finitely describable, but the language was just arbitrarily given.
Yeah, I have a question. Like, is there like any set that there's no machine that can
Yes, exactly. I'll give you
like
one.
a part of the empty set, I think.
No, the empty set is regular.
But how? Well, the starting point can be final point. Yeah, okay. So.
Yeah, so what would be the, can somebody show why the empty set is a regular language?
I mean, I can do it.
Yeah, but apart from you, let's see. Juan Sebastian? Or Juan Esteban? Amaya. Can you tell me why this empty set is a regular language? What would you have to do to show that?
No, profe, la verdad no sé.
Pero
But
no
Juan
idea.
Esteban, but at least tell me what you are supposed to do to show that, even if you cannot show it. Do you know what you're supposed to say to do?
No, profe, tampoco se me ocurre algo como para demostrarlo, la
But,
verdad.
but look at the definition. What does it say? This definition.
Queda el mismo conjunto, tal vez.
I'm not going to tell you, give me the solution, but at least, I mean, well, what you need to prove, what you need to show to prove that a set is regular. What does the definition tells you? Okay, so Juan Sebastián.
Sí, profe. Pues yo iría porque da el mismo. No sé si estaría bien.
Say it again?
Porque da el mismo. Como no, o sea, como lo metemos en... Da el mismo resultado, o sea, queda en el mismo estado, entonces podríamos decir que es regular, tal vez.
Yes, but okay, before giving a particular automaton, I want you to at least understand what you are supposed to do when I ask you the question. Is
Que tenga un solo estado.
no. In general, there could be, in general, what you are supposed to do. I want you just somebody to answer that question. If I ask you, is this a regular? Is what are you supposed to do?
Because the initial state is the same as the final.
No. Okay, let's go back. I think you are confused about something. Let's forget about for a moment about the empty set. If I ask you, show that A is regular, can you tell me what you are supposed to do or to find in able to show that a set A is regular? Jeremias?
Use the L of M definition. Like, if the set resulting of the definition of L of M is the same set as the set given.
Yes, exactly. So
That
another
is.
way to say this, if to show that A is regular, what you need to do is to find, to draw, or to define an automaton M whose language is A. That's what I wanted you to answer. In this case, as Joan asked, is the empty set. So A is the empty set. What I need to show to prove that the empty set is regular is to find an automaton, any automaton, whose language is the empty set. Do you understand that now, Juan Sebastian?
Sí, profe, me faltó esa parte.
Okay, exactly. Now we're gonna try to define. So now we saw all the definitions here. Now we know when M accepts X. This is the definition, and this is the language of M. Now think of any automaton whose language that will not accept any string, not even the empty one. Johan, I kind of know that you know the answer, so I'm gonna skip your answer by now. Let's say Santiago.
Shouldn't that be one that has no accepted state?
Exactly. That's one. Very good. So let's try to draw it somewhere here. So basically, actually, that one is an automaton. It has one initial state, but no accepting state, so you cannot accept anything whatsoever. Very good. Another one could be one that has an accepting state, but let's say this is P, Q, R, D, and so look at the automaton. It has a starting state P and a accepting state R, but its language is the empty set. Why? Juan Fernando?
Because you can go from the initial state to the final state.
Exactly, because there is no path from the initial state to a final state. So no matter what you do, it's not going to accept any string. Okay, Joan, you want to add something new to this?
Yeah, I have a question. So so there are machines that don't accept any string, but are there any strings that don't have any machines that can accept it? Because I can think of any.
Yeah, I'll show you one. So let's suppose that you want to accept the following this set. And this is an interesting question. So can someone read that set and tell me what it does? I mean, what kind of strings does it have? Maria Jose?
To read it, so I'm saying that the set, so it's a power to the n, a is power to the n, and b power to the n has to be where n is higher than 0 or equal to 0.
Exactly. So basically, this A has all the strings of the form A's and B's such that it has the same number of A's than B's. Okay, so for example, A, B is not in A, but A, B is in A. Understood?
Yes.
And now this is something that could be confusing, but I understand Johan's question. Johan say, of course, I might build an automaton that recognizes A, B, B. So A, two A's, followed by two B's, and this, right? That automaton will accept this one. And you can make another automaton that recognizes, let's say, AB, I mean the same one, A, B. So that automaton recognizes AB and AA, BB. And you might recognize also, I can continue doing this, A, 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 B, B, B. And now this automaton recognizes A to the 2, B to the 2, A to the 3, B to the 3, and A to the 1, B to the 1, and so on and so forth. But, Johan, if you want to recognize all the strings of the form A to the N, B to the N, you think I can do it? Certainly, I cannot do it without with this strategy, because then I will need an infinite number of states. And I do not have an infinite number of states because these machines are called finite state automata. So finite state automata means that you only have finite states. So at least that automaton is not going to work. Here, the automaton that I just draw, it has a subset of this. Okay? But not the whole set. Do you understand that, Joan?
Yeah, I understand.
So the question remains, is there an automaton that recognizes the set A? Is there an automaton whose language is A? In other words, is A a regular language? What do you think?
But if we make like a cycle and we make all states of acceptance and we define some random transitions, I think it can work.
But you might be able to recognize A star, B star, but how do you manage to keep the same number of A's than B's? Santiago?
Yes, I was gonna say that couldn't be possible because we have to remain with the same number of A's and B's to remain for the definition. And doing it as a loop could not possibly remain with that example as accepted, because you would have, for example, A and B, but if the input is A B B, they will not be able to pass through A since it's only capable from passing from A to B.
Exactly. Very good, Santiago. So our intuition basically is telling us, that's difficult. This solution will not work, the one that I just draw here. And the solution that Joan suggested is not going to work either because it cannot count the number of A's and B's so that they keep being the same. Jeremias?
Yeah, I think I got a question with what Joan said, because if you have, for example, an automaton with two states, the initial state and the final state. Let's say in the initial state there's a cycle with A, and if you reach B, you move to the final state in a cycle again. So wouldn't that be like accepted, like for that?
So say it again, Jeremias, can you draw
Yeah,
it?
it has two states. The initial one and the final is the other one. So let's say A makes it stay in the initial state like a cycle, and B goes to the final state, and then uh, it stays there, like it doesn't matter which is the input.
Like this?
Yes, like this.
Okay, so let's see if this is the automaton M that Jeremias suggested. The question is L of M equals to A? This is my A.
I have a
Santiago,
question.
answer that?
I have a quick question, please. When we have the this set A, like all the strings that come out have to have this property. That's what it means.
Yes.
Okay.
Not come out. Nothing comes out here. It's just it's accepted or not.
I'm using like the elements of A to create the strings, right? So I am a little confused here. Like A has this property. Does it mean that every element of A has this property, or like the strings
Exactly.
like?
No. A is the set of all strings on the form A to the n, B to the n. The n is the same for A and B.
So if I want to make a string of A, I could use like AB.
No, because that one AB doesn't have this form.
But I mean, there's an element in A that is AB, right? That's N1, and that's an element. I want to create a string that will be AB, for example. I'm concatenating two things. I'm confused.
No. Look, no. I think you are confused. Forget about automata theory. This is just mathematics. You are defining a set of all the strings on the form A, N, B to the N. But A and B are, of course, from the alphabet. Maybe that's what have you confused here. This is, and your alphabet is A and B. Okay? So your alphabet is A's and B's. Those are your symbols. And you want all the strings on the form A to the N, B to the N. This string that you propose does not belong to A. Maybe what you are confused is it belongs to, and we saw that in the other class, to A concatenated with A. That is true. If you concatenate A with itself, then AB is in A or A square, if you want. But AB is not in A.
Okay, so sigma is the set of elements, and A is like a set of strings.
Yes, A is going to be a set of strings. Yes.
Oh, okay. Now I get it. Okay.
Okay, good. Now, the question here this is a very interesting question by Jeremias. I hoping that Santiago can answer this question. Is the language of M equals to A? To the A there?
I would probably say no.
Yes,
Because
and you're gonna probably say no. What
yes,
you need
the reason being is that we have to change from one state to the other continuously, and doing that we only remain on a single state. Even though the input does tell us to move from one state to the other, it would not actually do anything because it would remain inside a loop.
Yes, but you have the intuition. Try to do the following. Try to find a string that is accepted by M, but is not in A. And that will destroy this equality. Because you will have an element here in this set that is not in this set. So these two sets cannot be equal.
Oh, sorry.
So that would be like, for example, BAB.
Was Santiago the one speaking or Jeremias? I don't understand.
Santiago.
Santiago. Okay, Santiago, continue. What string would that be?
For example, BAB could be one that it's accepted on the language of M.
Exactly.
But not in A.
BAB. Exactly. That one belongs to the language of M. So M accepts that string, but that one, BAB, is not in A. Jeremias?
So could we say that the language of this like it's a subset of, I mean, A is a subset of the possible answers that this gives with this automaton, right?
Yes.
All right. Now I get it.
And what you need is are the same. So yeah, any string of the form A to the, let me check this. It is not quite a subset, Jeremias, but only because this is n greater or equal than 0. That means that the empty string belongs to A. That means the string of the form A to the 0, B to the 0, which is the empty set. And your automaton does not accept the empty set. So in that case, we have the empty string belongs to A, but the empty string does not belong to the language of M. That destroys your inclusion. Jeremias?
Yes, so it will have to be greater than 0 for it to work.
Yeah, for your conjecture, yes, you have to be greater than 0.
Okay.
Anyway, but now you started to understand that there might be languages who are not regular, that are not regular. So, in fact, we will show in this course that AN, BN cannot be regular. That means that there is no automaton that can accept A. Okay, we'll see that in the next class. Johan, one question?
Yeah, I was confused, but now I get it. It's nothing.
Okay, good. Okay, so in this class, what we did was to take the intuition that we had from the previous class and define this formally. And now we have a formal definition of the notion of automata, finite state automata, sorry, and regular languages. In the next class, we're gonna see that this automata can be used to define actually quite useful structures, not just this toy example that I gave you here. Okay, so I'll see you in the next class. See you next Friday, and I leave you with
No se vayan ahí, por favor, muchachos.
Nicolás is gonna continue explaining the homework that Juan Esteban was asking. Okay. Okay. Bye.
Thank you very much for the class.
Bye.
Gracias, profe.
Bye, gracias.
Hi, teacher. Thank you.
Gracias, profe.
Bye.
Muchachos, una pregunta. Ustedes ven clase con Carlos Ángel, ¿cierto?
Ni idea, creo que no.
¿Cuál es su apellido?
No sé.
Ángel.
Ah, Ángel, Carlos Ángel. Creo que me suena.
No,
creo que
no está en computación gráfica, creo, o algo así. De pronto.
Que no ha entrado ni una vez, pero bueno.
No,
Si
si no ha
querés le
entrado.
pregunto, yo lo tengo en WhatsApp, si querés le pregunto.
Pues, si querés. ¿Dejamos de grabar y revisamos eso? ¿O que la tarea también quede grabadita? Prefiero.
Yo preferiría que la dejemos grabada, ¿no? Y así.
Aunque, no, espérate, la pizarra no se graba en Teams. No.
Pues entonces, no sé, alguien le toma foto de la tarea de ahí demostrada y
Pues
ya,
sí.
y la mandan por el grupo o algo así.
El poder de Microsoft no graba su propia